Now, I personally didn't interview for a lot of manufacturing engineering positions per se. The positions I interviewed were for mostly design engineering or electrical engineering or in reliability and test engineering positions, because that's something I kind of preferred over manufacturing. But despite that, I was still asked a decent number of manufacturing engineering questions. So based on the questions I was asked, here's what I think would work best for you to learn. Now, the manufacturing techniques used to make a product fundamentally vary based on the material used. For example, the mass manufacturing techniques used to make a tin can would vary vastly in comparison to that of, let's say, a water can. Or the mass manufacturing techniques used to make a metal sheet, once again, vary quite a bit in comparison to that of, let's say, a grocery bag. Now, if you compare the two examples, what is the most obvious difference between the former product and the latter product? Well, it is the material, isn't it? Metals and polymers. Now, a few ways of manufacturing metals would be casting, such as die casting or investment casting. Forming is another one. Machining, such as CNC machining, is pretty popular. And finally, joining, such as welding. Now, if you look at plastics or polymers, on the other hand, the most common example you could give for an example of plastic manufacturing would be injection molding. Now, study up on injection molding because you will be asked about this during your interviews. So study up. It's good to know. Another one would be blow molding. Thermoforming is also a pretty good thing to study because you might be asked about it too. I was personally asked about it, to study it. Other concepts such as rotational molding, and finally the most infamous one, additive manufacturing, aka 3D printing. Die casting versus injection molding. The concept of manufacturing is relatively the same here. So you start off by melting a certain material and then pushing it inside a cavity or a mold using a sort of piston or a high pressure pusher, and you fill the cavity up to a point where it's pressurized inside, and then you let it cool and solidify. Once it's cooled and solidified, you then open up your mold, and then you take the piece out. You just extract it using a plier, you just pull it out, if you may. And that's kind of the idea between die casting and injection molding. So what is the difference then? What is it? The most obvious difference between both these manufacturing techniques is the material used. In die casting, you use metals, and in injection molding, you use plastics. In die casting, you take your metal, your solid metal, send it into a furnace, melt it out, get liquid, and then you send it into your cavity to solidify. In the case of injection molding, the idea is the same, but you just have plastic pellets instead, which is first melted in a burner, and then you send liquid plastic into a cavity, which is then solidified. So if you think about it from face value, the concept of manufacturing between die casting and injection molding is the same. It's just that the material used is different. So I was asked this question during my first ever engineering interview for a full-time job. I remember the interviewer should ask me this question. She said, "What do you know about FMEA and DFMEA?" And I think I'd studied about it, but I'd blanked out when she asked me, and I had no idea what she was saying. And it was very awkward and embarrassing when she asked me that, and I just looked at her face like, "What the hell did you say to me?" Yeah, that was pretty embarrassing. So what is FMEA? Failure modes and effect analysis. It's a systematic methodology commonly used in product development and manufacturing. Using FMEA, you can identify and analyze potential failures and proactively find solutions to it before it actually becomes a real thing and you lose a lot of money. So let's say you were tasked to do an FMEA analysis on a specific system. So the first thing you would do would be to identify all potential failures in that system. Once you find that, then you solve with 3 metrics. The first one is severity, how severe the failure is. Second one is occurrence, how commonly occurred is this failure. And the third one is detectability. And you give it a rating from 1 to 10 for each of these metrics. Once you solve for the ratings, you multiply all 3 values. The solution or the final product of this multiplication is called the risk priority number. Once you get the risk priority number for each of these failures, you kind of send them from smallest to highest values, and then you find out which one has the highest RPN, and that would be the highest risk versus the ones with the lowest values, which would be the lowest risk. Sound simple? It's not too bad. Just study some more about it and you should be fine. Failure modes and effect analysis. So if I were to mass manufacture a plastic product, what manufacturing technique would it be? Well, injection molding, right? It's the most commonly used manufacturing technique for mass producing a plastic product. Well, some of the advantages of using injection molding are highly precise. It's very precise in terms of the products to create. Its mass production is very consistent, so it produces consistent parts over time. It's very versatile. You can create various designs, incredible. You got a plethora of materials you can pick from in terms of plastics and the polymers used. You can automate it, so you don't have to sit down next to it and constantly scrape on gawk and whatnot. It's like quite occasional when you do that. And finally, economies of scale. The more you produce, the cheaper your manufacturing gets, so that's great too. An example of a place where injection molding is very prevalent would be Lego. Lego creates these little bricks, and they make so many of them using injection molding. They have a tolerance of 0.1 millimeters, which is remarkable. So that would be a perfect example of injection molding. How to design a part for better injection molding? Well, some of the more common problems faced, or some of the things that occur when performing the injection molding operation, are air traps inside the mold itself, drag marks, burn marks, sinking, warping. These are things that you experience or notice during your initial injection molding operation. How do I approach the design? Some of the basic things that you could look at would be, first, increasing your wall thickness. Having a thicker wall would help mitigate the shrinkage that might occur during the cooling process of the object itself. The second one would be adding a fillet or fillet. Fillet would actually evenly distribute the stress across the corner of your object itself, so that kind of helps. Adding a rib would help make the corner of your object more sturdy. That's great. Adding a tapered design, such as a draft angle, to an injection molded part can be a useful design feature for various reasons, such as improving part ejection, or reducing friction during demolding, or simply enhancing the overall part quality. And finally, better material selection. Having a material that does not succumb to some of the problems that you might face in your injection molding operation will be preferred. So that would be the initial design considerations I would make when developing a product for injection molding. Some key factors I look at when picking a material for a product. Well, the first thing I'd ask myself is, what is the functional requirement of that material with respect to the component I build? Well, I look at some mechanical properties of the material, stuff such as electrical and thermal conductivity, wear resistance, structural rigidity, durability. I look at these concepts and make an assessment to see if this material that I pick would work well for the component that I intend on building. The next thing I look at would be cost. Well, of course, everything has to be within a budget, right? So cost would include cost of the raw material, cost of assembling the product, cost of machining it. All of that comes under cost. The third one is ease of manufacturing and assembly. Let's say a material was easier to manufacture, it would be highly preferred over a material that wasn't, because it's easier to work with, it reduces the complexity of manufacturing, and it's cheaper too. And finally, compatibility with other materials. Let's say you were asked to develop a product that was situated in a damp environment. Let's say one part of that product is made out of aluminum, another part is made out of copper. Let's say that both of them got in contact with each other, chances of galvanic corrosion could be highly likely, which could ultimately affect the structural integrity of the entire product. That would be a bad idea, right? So if you look at all these points together, I think this is a good starting point to answer this question. So yeah, that's how I would approach it. My favorite manufacturing technique would be 3D printing, simply because I've used it quite extensively during the course of my time at university via design teams or just my own personal projects. Some of the advantages of 3D printing are design flexibility. You get a chance to basically design anything you want within a certain volumetric dimension, of course. Very cost effective in terms of rapid prototyping and reduced material waste. If you compare 3D printing with, let's say, subtractive manufacturing, wherein, let's say, you have a milling machine and you chip away bits of a block, you're wasting a lot of material by chipping it away, whereas in 3D printing, you're basically adding material layer by layer. It saves basically a lot of material in the end. Some of the shortcomings of 3D printing manufacturing are layer adhesion issues, which ultimately lead to some wastage of material, warping or curling, stringing, or just a ginormous time it takes to complete your 3D print. To summarize, we started by talking about the manufacturing techniques for metals and polymers. We spoke about FMEA, die casting, injection molding, and a bit of 3D printing. However, if I were applying for a manufacturing engineering position at a company, I'd dig a little deeper into the manufacturing techniques used to build metals and polymer-based products. I'd also try to learn as much as I can about the manufacturing techniques employed by the company themselves to build their own products. For example, let's say I was applying for a battery manufacturing engineering position. I try to learn as much as I can about roll-to-roll formation or cell sealing or electrode assembly or battery pack assembly, stuff like that. Learn as much as you can about how the company basically manufactures their own products. I think you'll be able to kill the interview.